and welcome back to my channel. So in the previous videos we saw how to create a simple application in order to select the inputs for the simulation, and then we have added a table to do parametric sweep, in this case for the mass, and then we have added two callback function to control whether we want to run single or multiple simulations. In this video we're going to explain how to use the Simulink data inspector in order to control the plotting of data of our simulation results in a synchronized fashion, where we'll be able to directly zoom in or zoom out on the data on a subplots or on a single plot. We'll also be able to show and hide data and to save simulation sessions to open later. So it's very useful to do post analysis of simulation and to better control the plotting of our variables. So let's start. The first thing, we'll start by doing using the Simulink data inspector for a single run. So if we begin, we'll go to the callback function of the run simulation button pushed. Now I have removed the plot function because I want, in this case, to use the Simulink data inspector. So we will start by setting up our Simulink SDI or Simulink data inspector. We're going to clear all the already data which could be loaded to the Simulink data inspector. Next up, what I will try to do is to set my subplot. So I will add the subplot layout to 2 and 1, because in our case we need to be able to show on two subplots, so the values of the angle theta and the angular velocity theta dot. Okay, so let's create. Now we need to create a run, and this run will be specific to this simulation, to this run or to this simulation which is executed. So we'll use the function run create. Next, we're going to take the variable that we need to add it to this run in order to be able to plot it later. So the attitude will be the output or the structure which will contain the variables of or the result of the simulation execution. So we'll take from the output right here. So if we go here, so we can see that the ADG that we're getting as output will mainly contain the theta and the d theta. So we'll take the theta, and then we'll take all this output and then start in the attitude structure. Now I'll tell the Simulink data inspector, or the run in the Simulink data inspector, to add to this particular run the following variables, which are the attitude in this case. Next, I need to select or to get the ID of each variable in this output. So I will call the theta ID, which is equal to get signal ID by name, because I will going to use the name of the signal. And then I will take the run, which is this particular run, and then I will take the variable which is called theta here in the bus. Okay, so this will be my ID. Next, I need to take the d theta ID, or the derivative of the theta ID, which is equal to d theta. Next, sorry. Okay, so next, what I need to do, I forgot to add the Simulink SDR right here. Sorry. Okay. Next, I need to plot on the subplot. So plot on subplot. because we have set the Simulink data inspector to have a subplot of 2, 1. So we'll plot on subplot a variable that we have to define, which is called theta. So the theta will be equal to the Simulink data inspector. Simulink data inspector here. Sorry. Okay. So Simulink data inspector, and then we'll get signal, which is equal to theta ID. So the theta, the local variable theta, will be the extracted variable from this particular run using this particular theta ID. So I will do the same for d theta, and then I will plot the theta on the first subplot. I will use the same function to plot the d theta on the second subplot, and then I will need to show my Simulink data inspector, and by this we have all what it needs to execute a simulation, take the variable, create our run, and plot the variables theta and d theta on the subplot. So let's run this application again. Now we'll call the run simulation, and then we'll see that automatically it will create a run. However, we forgot to add a name for this run. We'll do it right now. So in this run, we have added the ATT structure, which contains the theta, which is automatically plotted on the first subplot, and then the theta dot on the second subplot. So as you can see, we can view and control the viewing of the data in a synchronized way, and then we can also use the feature from the Simulink data inspector in order to save this particular session to be able to open it up whenever we want. Okay, great. So now let's just return here a little bit. Let's add a name which is equal to single one. Oops, sorry. Okay, let's try to execute again the simulation, and then if we're on the simulation, it will open up the Simulink data inspector and will automatically add to this particular run the name single run. Okay, cool. Now let's do the same, but for the for loop or the parameter sweeping that we are doing right here. So it's very useful to analyze, as we said the last time, to analyze the impact of a variation of a certain model or a certain parameter on the system dynamic. So I'll take all of the stuff, I will put them right here. Okay. So I have already added the Simulink SDI view at the last, and in the previous video I was using another index right here, which is called, or right here it was called IDX. However, it was not exactly precise because every time we were using the same, we're using array of one dimension, so we just need to correct it to I right here. Now let's take all of this stuff and then we'll replace the plot here by all of this stuff. However, we need to do some adaptation of the code. So what we need to do first is to change the name of this run. So what we're going to do, we need to tell the SDI that for each run, for example, for the first simulation, I will need to create the first run, which is called run 1, and run 2, run 3. So it's run, basically it's run and then the index. So I can add run and then num2 SDR, and then I'll take my I, which is the index of each run. Now I will need to adapt this one to I. Next, so I can leave all of this stuff. I don't need to change it, and then we're good to go. Let's try to execute simulation to do perhaps some sweeping between 1 and 5 kilogram of the mass, and then let's start to do mass sweep. As we will see, it will automatically create run 1, 2, 3, 4, 5. Then it will plot all the data. As we can see, when we select the particular data, it will indicate in which run we have the selected data. We can zoom in, zoom out again. So this, as we can see directly that the first run right here was executed with the lowest mass value, so it was 1 kilogram. So we can see the less the mass, the more the damping of the oscillation in our system. So thank you everyone for seeing this video. If you like the content, please subscribe to my channel. In the next video, we'll try to use use a direct application of the parametric sweeping. However, we're going to build a feedback control law to control our pendulum, and then we'll try to take advantage of the parametric sweeping to try to find out the control gains that will optimize the error of our system. So see you next time, and thank you all.